All right, hell yeah. So someone had a question about how do you add, why can you add two things to both sides of the equation? And so what we have here is the generic form of a polynomial, and this is the process of completing a square. And so in this first step, it's nice to just get x squared all by itself. And so we take this and then just divide it by a. Divide each term by a. A divided by a is 1. And then we have b over a, and then c over a. And then over here we would have 0 over a. And so now I think the first question is, you know what I mean? Like what is this equation? That was the first question that I would ask. Is like first, like what is this equation, and why can we balance equations? Alright, for this video, we need some sort of equation that represents what we're going to do, and I just thought this right here was a pretty good example. So we're going to have kind of, here's what we're going to have. We're going to have like the ground, and then we're going to have a cliff, and we're going to throw a, we're going to have an upward velocity of 10 meters per second. And we're going to have some sort of thing that goes up and then down. And we're going to be at a height of 15 feet. And the kinematic equation of this, well, we would have gravity. And for this, I'm going to have gravity be 10 meters per second. And I'm going to put my position 0, 0 here. So this is going to be, now here's what this would look like. But what we want is just a graph of the height. I'm just going to say height. Y is a function of time. So we want the height, and then here's time. So at time 0, we're going to have our height over here. And for this, I'm going to set this be the negative y direction. This is going to be the positive x direction. Just so my gravity is going to be, in the positive direction. And so that means that this height right here is negative 15. So on this graph right here, I'm going to say this is still negative y. And cool. So we're going to start off at negative 15 meters. With an upward velocity, we know that the velocity is going to change by 10 meters per second after a second. So we're going to go from a speed of 10 to a speed of 0 meters per second, average speed of 5 meters per second. This average is the most important part of that. Hey, we're going 10, we have a speed of 10 going to 0. We must have to have an average over that 1 second of 5 meters per second. And we traveled for a time of 1 second. So we're going to go to negative 20 meters. Booyah. So that's going to be kind of this height right here, negative 20. And that's going to happen after 1 second. So I'm just going to put 1 second here. And so we're going to be here, and then we're going to have a height of 20. Now in the next second, we're going to pick up, we have a speed of 0 meters per second, pick up a speed of 10 meters per second after the next second. So by symmetry, we're just going to be back over here. Average speed of 5 this way. Now from here, we have a speed of 10 meters per second. In the next second, hey, we're going to have a speed of 20 meters per second, average speed of 15 meters per second. And now you can see why I chose 15 as my height, because in the next second, I'm going to hit the ground right there. Booyah. And so here is, now the only thing not to get confused, this is not a function of what the path would look like if we threw it this way. I'm just pretending like I'm throwing this rock straight up and straight down. I'm just saying that, in this graph, sure, maybe I do throw it this direction and it has some sort of a velocity that way and hits. But all I'm interested in is the fact that it's going up and it's going down. And that's what this represents. If I had this as a function, so like right here, all this says is that whatever I threw went up and then went down. And so here it's very visual to see a projectile kind of traveling up then over, so you can see that. But you could have just thrown this straight up, straight down. And then so here is still here's our equation of the function of height as a function of time. In a second it's up there, in another second it's right there, and in the third second it hit the ground. Alright, hell yeah. So, but this is good because we get an equation, so we can say that, so usually you're just using your kinematic equation that says like y, you know, as a function of time is going to be 1/2 the gravity, so that's going to be 1/2 times 10. I'll just write it as, it's going to be 5t squared plus your initial velocity. That's going to be negative 10t plus your initial position, and that's going to be minus 15. So this is the generic form for the kinematic equation. And let's derive it. You know, I mean, if I have, because the first equation you should always write as acceleration is change in velocity, change in time. You know what I mean? And just know that this is going to be your average acceleration. Or if acceleration is constant, this equation applies. And then the other equation is velocity. Definition of velocity is change in position, change in time. And just know that it's either a constant velocity or an average velocity is what makes these equations work. Now their derivative form is just dv dt, that's acceleration, change in velocity, change in time. Velocity is dx, change in position, change in time. For projectile problems, also, you know, it's dy dt, because this might be velocity in the x, you know what I mean? That's going to be this direction. And this might be velocity in the y, kind of the direction we're more interested in. So, hell yeah, those are our two equations. Alright, so what you do is that you, basically get dv dt, and that's equal to this 10. The value for the acceleration is constant, and then you're going to separate variables. So you're going to get dv is 10 dt, and then you integrate. You're going to get v is equal to 10t plus a constant. Now this is an equation for velocity, and so, you know, it's velocity as a function of time. So at time 0, what's our velocity? Well, we said we had an initial velocity of 10 meters per second. So, you know, c has to be 10. Oh, and, oh, did I do this wrong? Oh, no, my bad. I said that this is the negative direction. So we actually have a velocity of, so at t is equal to 0, we have negative 10 as our velocity. So we're going to have 0 plus c. So c is going to be negative 10. Okay, so our function for velocity is going to be 10t minus 10. Cool, and then we can do the same thing by integrating velocity. We can say velocity is dx dt. That's going to equal 10t minus 10. Separate variables and integrate, and we're going to get x. We're going to get the position as a function of time. This is t squared divided by 2, so that's 5t squared. This becomes negative 10t, but plus a constant. So when we throw in 0 for here, do we have a position? Yeah, we're going to be at negative 15. So our plus c has to be minus 15. And so that's, you know, maybe I shouldn't have even gone over that. But nah, you know, it's good to at least go over it so you can be like, okay, I get where this kinematic equation comes from. The generic form is 1/2 the acceleration. Acceleration was 10 divided by 2 is 5. T squared plus the initial velocity, t plus the initial position. And our initial velocity was just a negative 10, and our initial position was a negative 15. Cool. So now we have an equation, this. So why I'm doing this is because, like this, we're setting this equal to 0, and you're like, well, why and what gives? Like, because isn't this just an equation? Couldn't this just be a function? Like where you just have y of x is equal to ax squared plus bx plus c. And then if I threw in x is equal to 0, if I threw in, so y of 0, or y when x is equal to 0, or just y at x equals 0, just a bunch of different ways to say, hey, I'm evaluating this function at x equal to 0, well, that's just going to equal c. So, and you could have, you know, y at 1 is going to be a plus b plus c. And then y at 2 is going to be 4a plus 2b plus c. You know what I mean? So we have just, we basically have a function. So now the question is, why would we set this equal to 0? And what are some applications where we would do this? And a kinematic equation is one of them, because we have equation for height. So this side is height. Cool. And then what's our input? Time, like in 0 seconds, 1 second, 2 seconds. And then we kind of know our height. And we just know from practice that if we throw something up, throw something down, it's going to hit the ground at some point. And maybe we want to know the time that it hits the ground. Cool. So what we're going to say is at the ground from our coordinate system, that ground is 0. So that's a height of 0. So then I get 0 on this side is equal to 5t squared minus 10t minus 15. Cool. So that is why we can have an equation that's evaluated on one side can be 0. This could be any number. I mean, maybe you want to know when it hits, up on top of this car, and this car is like a, 1.5 meters, big SUV. You're trying to hit it, and then so you want to know the time you're going to hit a car. I don't know why you do that. It sounds like you get in trouble. But anyway, and then, yeah, so that would be 1.5 right here. You'd want to evaluate the height. When the height gets to be 1.5, what's the time? And so that's the whole idea of the quadratic equation, is that at some point you have an equation, and you want to know not when the time is 0, but you want to know when the equation gives you 0. And it's kind of a bizarre thing. So I'm going to do one other example. I was like, let's say you started a business, or let's say you started a job. I just did this one. It's just like, well, let's say, yeah, it is decent. So we'll do 6x squared minus 2x minus, I don't know, maybe minus 10. Okay, hell yeah, make it kind of interesting. So this is, and then you have y as a function of x. And we're going to get back to this one, but it's just good to have kind of simultaneous equations. I mean, just two examples where you can kind of wrap your mind around why you would make something equal to 0. All right, and so this equation is going to be your salary. And I was just thinking, maybe you're just going to work for the weekend. But this job requires you to actually pay for your own equipment, you know what I mean? And each day you're going to have to pay, like you're going to have to buy more and more equipment. It's just kind of fascinating. So, and this is one of the rules that I use for anytime I get a polynomial, especially a quadratic. I'm going to quote this as the -10, -2, -1, 0, 1, 2, 10 method. You know what I mean? Typically, it's just the 0, 1, 2 method, but then, the -1, 0, 1 method, -2 to 2, you know what I mean? But if you put in 10, like all these are very, so this is what we're getting at. All these are very simple things to put in values of x. So here's my values of x, and I'm just going to say when x is 0, hell yeah, you just cover those up. And booyah, we get a negative number. That's all I'm doing. I'm just saying that we're going to get a negative. So now let's go over to, and then the other thing going into this is just know that every polynomial is either going to start at positive or negative infinity, and it's going to end at positive or negative infinity. So it could start at negative and go to negative. It could start at negative and then go to positive. This is your classic, well, this would be x is equal to -x squared, you know what I mean? And then you could start at positive and you could go to positive. This would be your y is equal to x squared, classic. This would be your y is equal to x cubed. And you could also start at positive and then go the other direction. So, and that's going to be, something else. But anyway, but hell yeah. So just in general, polynomials always end at infinities. And so that's why I put in 10 and -10. And so let's do that one next. You know what I mean? So if I throw in 10 here, 10 squared is going to be 100. Hell yeah. And then times 6, that's 600. Okay, that's going to be a huge positive number, but now I'm going to subtract 20, subtract 10. Okay, I'm still going to have a huge positive number. So here's the take-home point. If I had a negative and then a positive, somewhere in between here, there's going to be a value that makes this perfectly 0. Okay, so that's what this method is. And so let's throw in y is equal to 1. If I have 6 minus 2 minus 10, well, I'm going to have a negative number there. How about when I throw in 2? I'm going to have 2 squared is 4. 4 times 6 is 24. Minus 4 minus 10. That's minus 14. Whoa! I get my first positive number. So now I know that I have, and this is what the math term, you have a root between 1 and 2. But I don't like to use those terms like roots. You know what I mean? You just, like that's, like somewhere between 1 and 2, when you throw that value in for x, that's going to generate 0. So maybe it's 1.5. You know what I mean? So sweet. And because it's a quadratic, we're probably going to get a couple solutions, so let's go the other way. Let's do that same thing. You know what I mean? Because polynomials start and end at infinities. Well, let's see if this ends at negative infinity or positive infinity. When I throw in negative 10 squared is still 100. So this value is still positive 600. Oh, hell yeah. And then when I throw in negative 10 right here, this is going to be a positive 20. Okay, and so just subtracting, this is going to be hella positive. Okay, so now I know that there's a solution. I mean, I shouldn't have even said solution, but yeah, there's a solution, there's a root, or there's just a value between 0 and negative 10 that when you throw that in for x, it makes this 0. Okay, hell yeah. And and let's see if there's any difference going this direction. Because if we throw in, I don't think there will be. If we throw in negative 1 here, we still get positive 6, and then positive. Oh no, we get positive. It's close. It's close. If I made this one like 6, our root would be in between there. But we got positive 6, positive 2. That's going to be 8 minus 10. This is still negative, but it's close. The root. The root's closer to negative 1.25. Over here, it might be closer to 2. So anyway, so our roots can be, it's not symmetric. This graph's not symmetric. The other thing with quadratics is this lowers it. So we're going to have, this lowers it, this moves it to the right. So if we have a negative, it shifts it to the right, kind of opposite of what you would think. This for sure just lowers it. So then you're going to have something like that. And that's kind of what we have, is that we have, here's 2, here's 1, and here's negative 1, and then here's negative 2. So that thing's going to pop right there and then pop out right there. All right, hell yeah. All right, I don't know if this video is useful at all. Hopefully we'll make a quick, quick start to this. But now let's talk about what this equation could be. So this equation, what I wanted to be was the money that I'm going to pay you, but on the first day, you know what I mean, or just on day 0, like right at hiring, you know what I mean. Hey, you're gonna have to give me $10. It was $10 just to like, hey, throw your money in. So now you're out 10, and then. And we're not doing the area under the curve. We're not. All we want to know is just like, hey, when's the first day I actually don't pay the company? Because right off the bat on day 0. So if I throw an x, so then let's get this. So this value is going to be their money. X is going to be days. So at 0 days, you got to pay me $10 to join this company. But after the first day, let's see what happens. I still think you owe me money because maybe you got to buy materials and supplies. So we're going to have 6, if this is 1, this is just 6 minus 2 minus 10. And we're going to have 6 minus 12. Hey, you gotta pay in $6. So the second day, you got to pay $6. All right, let's see if you make any money the second day. That was your first day of work. You had to pay $6. So when x is equal to 2, this is going to be your second day of work. Let's see if you actually get paid. 2 squared is 4, times 6 is 24, minus 2 times 2 is 4, minus 10. So we have 24 minus 10. Oh, hell yeah. So you get paid $10 on your second day. Now, now what we're going to say is like, hey, you're just working continuously. You know what I mean? I don't know, maybe it's a robot that we're going to pay in the future, and we actually have to pay the robots every, you know what I mean, every, continuously, kind of every second. So somewhere between the first day and the second day, you know what I mean? Like, I don't have to pay that robot. You know what I mean? Or at some point during that day, you know, it flipped from that robot paying me to that robot I actually have to pay it because it's working. So that's all I was getting at. So yeah, and that's the roots. Somewhere between day 1 and day 2, this value is 0, where the worker, you don't have to pay me, I don't have to pay you. Cool. Alright, so that's where we set this equation equal to 0. So we can set it equal to 0 on this side, 6x squared minus 2x minus 10. And we can, you know, just kind of put the 0 on the other side. Doesn't really matter. Okay. Alright, so, but this is a huge difference between this function is the money you're making, x is in days, minus 10, compared to this. 0 is equal to 6x squared minus 2x minus 10. This equation, if I, because right here, the first thing we do is divide by a. So let's do that on this. Let's say the first thing we do is y of x, divide by a, but you got to divide by a everywhere. We even did 0 divided by a over here. So here, I would have to do this function divided by 6 is equal to 6 divided by 6x squared minus 2 divided by 6x minus 10 divided by 6. And then I would have this function divided by 6 is equal to x squared. Finally, I get this x squared minus 2/6x minus 10 divided by 6. But now, like, hey, this function was supposed to be the dollars I was making at any given day. And now I just divided it by 6. So now this function, like, totally changed. You know, now this function is, if I take, is the dollars per day divided by 6. And if I take this as, like, maybe some new function, you know, like this is going to be, hey, the money I make each day, but then divided by 6. Or the money I have to pay the company divided by 6. You know, it becomes kind of nonsensical. But now we want to know, like, why, if I set this value to be 0, why then can I just divide everything by 6? Why can I start doing that on both sides and still get something useful? I don't even know. Yeah, and one of the only examples I could think of was just like, well, I don't know, let's say you had 4x is equal to 0. I can't think of why you'd want to do this, but, you know, I don't know, just as an equation, like what satisfies this equation? Well, if x is equal to 0, hell yeah, you can check that box. These two are going to be the same. Well, can't we just say 2x is equal to 0, and then x is still equal to 0? Okay, and so how to get from here to there is we just divided by 2. So 4x divided by 2 is equal to 0 divided by 2. I don't know, that's maybe I'll come up with better analogies, but I mean, you're still, like this, so this is different because you're saying, hey, somewhere between day 1 and day 2, when x is equal to 1 to 2, like, hey, this value is going to be 0. And so I just want, like, that. So that's the process of, like, hey, I want to know what that number is. And so then, I don't know. You know what I mean? We have this side equal to 0, and then this side also equal to 0. Let's say we just knew that value of x. And let's pop it into our calculator. So we have 6x squared minus 2x minus 10. Just kind of quickly graph it. We're going to get a 0 value on this. So we're going to be left bound, left bound, right bound. And then, yeah, so our value for x is going to be 1.468. So 1.468 days, that's when, you know, you won't owe us any money, but we don't have to pay you any money working for this company. Cool. So if I threw that value in here, that would be 0 is equal to 0. All right, hell yeah. But now I can move things around, you know what I mean? I can get this 10 over there, but when I do that, I'll have a 10 over here, and then I'll have 6x squared minus 2x. If I throw in that value of x is 1.468, this side will equal 10, and then this side will equal 10. So we still have like an equation. This equation has to be balanced. Alright, hell yeah. So now I was thinking, well, let's just do something to this equation. Let's add 100 over here and 100 over here. We said before we did this side was going to be 10, this side is going to be 10. So I think that's kind of the take-home point, is if you do have an equation with, you know, numbers on one side and numbers on the other side, then you only have one parameter going on here. You know, even though it's part of a function where you have like, I guess a function is where you can change this this value to be a lot of different values. And then, cool. But then even that, let's say you have a function for something, don't just assume it's going to make sense at positive, especially if it's a polynomial. You know, it's for sure not going to make sense at positive infinity or negative infinity. Because even if we go back to this example, like, you know, cool, it's going to hit the ground at some point, so the time can't be positive infinity. And then also, if it didn't hit the ground, you know what I mean, and you made a hole all the way to the center of the Earth, well, this equation is going to be no longer valid. Your acceleration is going to change, and so just know that any equation, and for the kinematic, it's not going to make sense if you have negative time. And so just keep that in mind, is that even though you have a function that is a polynomial that, you know, starts and ends at infinities, it might only have like a usefulness from like there to there. Sometimes even from just there to there, like that's what you're going to be doing with it. So then, yeah, for sure keep that in mind. Okay, hell yeah. So so this is different than a function because we're just assuming one time. And if we go back to the function, it's where the function was going to be $0, where I don't pay the company, you know, the company doesn't pay me. So that was the situation for this equation. And the x value is going to be the days that happens. Maybe I could have changed this equation where, hey, I have to work like actually almost 2 weeks, maybe 14 days before I have to stop paying for you know, supplies and stuff I need to actually do this job. Alright, hell yeah. So now, cool, so we can add things on both sides. We can understand that the second we put a value here. Alright, so both sides are going to be, you know, both sides are going to be equal. You know, we do have an equation. It's different than the function. When you have a function, obviously this value, whatever that value is going to equal this side. But when you have a function, you haven't chosen a value. So when we actually choose a value, I mean, when you actually have a value on this side is equal to something over here, even if you have, you know, a variable, like this does indicate a value over here. You know what I mean? So this x is only one value. And I think that's the crazy thing about math, is just like, well, does this x represent a bunch of different numbers? Or at this point, does it only represent one value? So I'm going to write it again, because I swear, I get, so we have f, if we just have a function of x is something something x, but then we can have this, f of 0. You know what I mean? So now we still have the same thing. But this is a little bit different. This would be when this value is 0. Heck yeah, you're going to pop out a value. Yeah, so that's even, it gets me confused every time. But what we're saying is that this function, this f of x, is 0. So we're going to put 0 right here is something something x. And now we're going to try to find, so x is going to be just one value. Cool. So that's kind of like the generic form of a function, how you can actually set this x equal to 0, or you could set the function equal to 0. And that's what's happening when we solve for quadratic equations. We're setting this side equal to 0. And hell yeah, because I think there's a lot of times, especially in your calculus, you'll have y is equal to something something x, and then you're just like, well, why do I set this equal to 0? Why is that, how are these two related? Well, this can be any value of x, but the second we do this, you chose one value, at least one. If it's an x squared, I guess I kind of messed up on saying that. Well, booyah. There's actually two of these values of x. Alright, hell yeah. So I got to burn out the rest of this video, but I do have a plan. I'm going to try to do 30 minutes more, hopefully no more than that. So let's go back to this kinematic equation. Always good to have two functions that we're going to do the same thing with. And so what we're saying is this is the function of the height. So again, we have f of x is equal to something something x. This is the height. You know what I mean? This is the time. So that's why I don't like math, because it's like, it's in generic form, and it's just like, well, I don't see that this is the height, something, something, time. But you know what I mean? It's always good to do that, to be like, oh, now I kind of see it. And then so when height is equal to 0, and you're like, oh, well, that's when f of x is equal to 0. Technically, that's what that would be. So anytime that you do stuff with math, like, do it intuitively, go through the numbers, and then see if you can go back and be like, oh, yeah, that's kind of technically what I did. Cool. And that's how I've been learning. That's kind of my strategy for this last year, is just like, hey, do the things with the numbers that you know what to do, but then step back and be like, what did I just do to those numbers? Cool. All right, so then we have the height is equal to 0. Where it hits the ground, this side is going to be 0 something something t. Cool, so let's do that. So here's our equation for height. We're going to say 0 is 5t squared minus 10t minus 15. All right, hell yeah. So now we have something. And now we can use that negative 10, negative 2, negative 1, 0, 1, 2, 10 method. Let's throw in 0. Our height, so this is 0 is equal to negative 15. And maybe I'm just looking at this side, you know what I mean? So when I throw in 0, I get negative 15. When I throw in t is equal to 1, I get 5 minus 10. Okay, but minus 50. So yeah, I'm definitely even more negative. So just right off the bat, I see that. When this is 2, this is going to be negative 20, negative 50. That's negative 35. All right, but let's throw in 2 here. 2 squared is 4. Oh, 4 times 5. Well, and that's just 20. So if I throw in t is equal to 2 here, bummer. You know what I mean? But this, why I choose these values is because they're kind of easy to do. I can do 2 squared. That's 4. I'm never going to mess that up. 4 times 5 is 20. So then I have 20 minus 20 minus 15. Still a negative. All right, let's crank it up. So 10 squared is 100. This is going to be 500 minus 100. This is all. And then minus 15. Okay, hell yeah. Now this is going to be hella positive. And let's finish the deal. You know what I mean? So that was kind of to get us started. Let's try t is equal to 3. And we're going to have 3 squared is 9 times 4 is 45. So we're going to have 45 minus 30 minus 15. Whoa! This actually, sometimes you stumble right across it. It gives you your 0 value. But let's say we did t is equal to 4. We're gonna for sure be a positive. 4 squared is 16 times 5. I don't know what 5 times 16 is, but I can have 16. 8 times 10, so that's 80. So we have 80 minus 40 minus 15. Well, for sure, all I'm doing is positive negative stuff. So this is going to be positive. Cool. So I have a check that my value, my solution, my root is going to be between 2 and 4. We go from a negative to a positive, and we just stumbled across the right answer right there. Now, it's going to have 2 roots, one imaginary, one like in real life, and so we can definitely do the imaginary root. Okay, so we're going to do that same thing, and yeah, where should we start? Well, let's just do this negative 2. So we're going to do negative 2 is going to be negative 2 squared. This is going to be positive 4. Okay, hell yeah. So we're going to have 20. We're going to have 20 oh, maybe I should have started with -1, but I was just using my intuition and it's kind of wrong. But no, this is going to be hella positive. That's all I'm getting at. Like, can you see that? Because this is now positive 20. -2 times -10 is another positive 20 minus 15. So hell yeah, that's positive. So we know we have a root in between here. So between 0 and -2, we're going to have an answer. How about -1? We're going to have 5, positive 5. This is going to be positive 10. Whoa! So we have 15 minus 15. We just stumbled across our root. So our two roots on this are at 3 and -1. Cool. When x is equal to -1 and x is equal to 3, those are our roots. All right, sweet. And so that's what I wanted to do for that. That was just kind of more of like, hey, we have a function. Why do we set it equal to 0? And why are we trying to find that value? And what does it mean graphically? Well, that's going to be the time. Again, it's going to take 3 seconds for that to hit the ground. Booyah. And if it wasn't 100% right, I would have said between 2 and 4 seconds. You know what I mean? Even if this was positive and this was negative, I would have just said between 2 and 3 seconds. Just kind of get that guess. Okay, so now for the second part of the question, like, why do we add this term? You know what I mean? We understand that we can add 2 terms on both sides, but why? So that's what we're going to do right now. All right, hell yeah. And this is completely different. So now we're going to start drawing some boxes. This box is going to be x plus 1, and this box is going to be x plus 3. For here, I'm just going to say x is 5. So cool, this is going to be, let me just divvy this up. And if this is 1, 2, 3, 4, whoops, I didn't draw this right, but there you go. So x is equal to 5, and then we have plus 3. So I'm going to say x is equal to 5, so we have 8 here. And then we have this is 5, 1, 2, 3, 4, 5 plus 1. So sorry, so that's my box right there. All right, booyah. So those are the x's every 5, and then we have plus 3. So we have a box with an area of, this would be 6, and this would be 8. So we have an area of 8 times 6. That's going to be an area of 48. Cool. So now what we can do is like, hey, let's multiply these two things together. Or how do I want to do this? Yeah, let's do that. We're just free-forming, but I do have a plan for this. So if we do this and we FOIL these through, we're going to have an x squared plus 3x plus 1x plus 3. And this is going to be x squared plus 4x plus 3. Now this, when we throw in x is equal to 5, let's try it out. We're going to have 25 plus 20 plus 3. What do we get? We get 45, 46, 47, 48. Hey, we get 48. So that was a totally different way. Well, I don't know. This was just 8 times 6. We got 48. This, we put it together and we got it into that form. Okay, now here's what we could do. We could say this is x. We could go to here. This box right there, this right here is x plus 1. Cool, so the area of this box is x plus 1 squared. Okay, hell yeah. And then what's this extra area? It has a height of x plus 1, and we just have 1, 2. So we just have 2 right here. And we could get technical and say if x is equal to 5, this is going to be x minus 3. I mean, so just a couple different ways to write this. We don't have to get too crazy. But yeah, let's get a little bit nuts. So we have, this is the area of both of these still is going to be 48. And it's going to be x plus 1. It's going to be this box squared plus this box, which has a height of x plus 1 times 2. So let's do this. How I FOIL this, I just say, hey, this is x squared and this is plus 1 squared. I guess I'll write it like that. And then I multiply these and say we're going to double it. So this is going to be 1x, it's going to be 2x plus 2x. That's how I do that fast. Slow process is probably, better, I don't know, you would have x squared plus x plus another x. That's where we get that 2x. And then we'll just have 1 times 1 is 1 squared. Cool. So that's why this term is, these two terms, you're going to have basically three full terms. Those are the two easy ones. And then this times 2. And that is a better mental method, this times 2, because then you can kind of understand when both these values, when you have an x plus 1 squared, you're going to get symmetry on this middle one. You're going to have x plus 1. It's going to be 1x, but two of those. It's going to be 2x. So x squared plus 2x plus 1. Okay, so that's that term. And now we're going to add it to 2x plus 2. Cool. So let's see what we have. We have an x squared, we have plus 4x, and then we got plus 3. All right, sweet. So we have another way to write this. You know, we have x squared plus 4x plus 3. Let's see what it would be. If x is equal to 5, we're going to have 25 plus 20 plus 3. Oh yeah, we just did that one. Oh, and we got the same same equation right there. Hell yeah. Now, when it comes to the quadratic, this part of the game is called completing the square. You know what I mean? So this thing's not square, it's a rectangle. We came up with one square, but then we had to add, you know, something else on. All right, hell yeah. So let's redraw this one. So we're gonna have x plus 1. We're gonna have 4.5. So that's 5. So that's x plus 1. 4, 8, 5. 1, 2, 3, 4. 1, 2, 1, 2, 3, 4, 5. Oof, don't have this drawn to scale. Anyway, so this is going to be x plus 3. So x plus 3 is right there. And then, so we have x plus 3, x plus 1. And we multiply these together. X plus 1, x plus 3. We get x squared plus 3x plus 1x plus 3. So we get x squared plus 4x plus 3. Okay, so and we get 48. So that's how many squares are in here. So if we go to you know, a square is that. That's 1. You know what I mean? And then this block has 4 blocks, and it's 2 by 2. This is a 1 by 1 square. This is a 2 by 2 square. And then so you would have 3 by 3, 4 by 4. And so we go 1. How many blocks are in here? 4, 9, 16. So our squares are 1, 4, 9, 16, 25, 36. So this is 6 squared. 7 squared is 49, 64, 81. Cool. So we got a value of 48. Where does that fall? It's really close to a square, but it's a little bit less. Like, so this value right here in terms of squares is 7 squared minus 1. Cool. So, you know what I mean? So that's also how we could write this. And even from our graph, what did we say? X is equal to 5. And over here, you know, we said this was x equals to 1. And we'd be like, well, what is this? This is 2. How do we write this as x? Well, that would be x minus 3. If x is equal to 5, then there you go. This is x minus 3. What's 7? That's going to be x plus 2. So this would be x plus 2 squared minus 1. So that's kind of, you know, so that's the process. And I'm glad I did that because I don't know. I'm just kind of on the fly, but because we're going to solve for this, but it's just so fascinating that we can do it the other way. We have an area of 48. We can see that's not a square, but 49 is pretty close. And so then we're going to have, you know, 7 squared minus 1. But the other way is we could have gone to 36. So we could have gone 6 squared plus 36 plus what? 36 plus 12 is 48. And then this is going to be x plus 1 squared plus 12. Okay, hell yeah. And that's what I wanted to do over here. I wanted to be like, well, let's say we just did x. This is x plus 1, x plus 1. That's a square. And then what would we have to add right here? Well, this is a height of 6. This is 2. You'd have to add 12 units right here. But this we just defined as x minus 3, and then we got kind of these components out of it. But okay, so hell yeah. So we could also say that 48, or that this is the area of that, x plus 1 squared plus 12. And we could make x anything. Maybe, I don't know, maybe it only works when x is equal to 5. No. My bad. This has to be equal to 48. So yeah, this is a very specific, like if the area is 48, x is going to be 5. And yeah, I'm glad I made that mistake, because it goes back, you know what I mean, to what are we talking about? Are we talking about the function, something something x, or are we saying, this side is a value, and then so x is one value. In this side, x can be a range, and then this, like, both these sides can be, positive. Both of these sides can be positive to negative infinity because it's a polynomial. But the second we choose, some sort of, in this case, area, then this side is locked in. So we chose 48 for this side, something something x. X had to be 5. So that's what we're doing there. Okay, hell yeah. All right, so how do we do that graphically? So I'm just going to get this equation. We said this was equal to 48. We said 48 was equal to x squared plus 4x plus 3. Cool. So let's do that same process. I'm going to get x squared plus 4x plus 3 on this side is equal to 48. So I just rearranged it. Now I'm going to get... we're going to do this two ways. You know what I mean? I think we'll do it we'll do it this way, because I think it's like, let's say I could just choose anything here. You know what I mean? Let's say I have a supply. Let's say this isn't plus 3. It's x squared plus 4x plus 100. Cool. And then so the process of completing a square is you have to get something that's x. This middle term is the most important, because if I do plus 2 and then I square this, hell yeah, what were we going to get? We're going to get x squared, 2 squared, that's going to be 4. And then this times this, but double. So 2x double is going to be plus 4x. So this is what we get rearranged as 2x plus 4x plus 4. Hell yeah. So we had a supply of 100, you know what I mean? All we needed was 4. So let's this one is going to, and then maybe you should do this every time. Supply yourself with 100 over here. Don't put it on both sides at all. Just say, hey, I just want to change this value. I know it's not going to be the right value to square it, but I'm just going to take from it. So now we can say x squared plus 4x plus 4 plus 96. See how now this is 100? And now I can do that process. X plus 2 squared. And then just, just run through it. It's x squared plus 4x plus 4. Oh, that's exactly what I have. And then I have plus 96. So this equation can be written as x plus 2 squared plus 96. Cool. And I took 4 of those out of the 100. And so this is a cool one because I have 3 here. It doesn't feel like I can take 4 out of... I only have 3. How can I take 4 out of that? So that's kind of where, you know what I mean? We just made up that you could just, change this to 4. Let's do that. X squared plus 4x plus 4. Cool. Now we know this is going to be x plus 2 squared. And we're totally satisfied. But what did we do here? Well, we had to actually add 1 to this side. So if we added 1 to this side, we had to add 1 over here. So I know I'm doing this fast, but no, this is good because I think doing this on the fly is just way better than going through something. And I think that's going to be the easier way to figure out a square. So let's go back. We have x squared plus 4x. We have plus 3. This is what we had this was the equation that we had. This was equal to 48. Okay. And in our generic form, it was going to be x squared plus b over ax was equal to negative c divided by a. We already got that term over here. We don't have anything here. You know what I mean? So then, I don't know, put something there. You know, put 100, same thing. And then when we do this, hell yeah. So let's do that process. We have x plus, this has to be half, b over 2a squared. And then when we go through this, we're going to have x squared plus, we're going to have double that times x. So we're going to have b over ax. And then we're going to have plus, this term has to be squared. So b squared, 2 squared is 4a squared. Cool. So this was like a, that was this 4 in this scenario. You know what I mean? We only had 3 to take away from, and we needed 4. In this situation, we don't have any to take away from, but we needed this. You know what I mean? So if we need this on this side, and we add it to this side, 4a squared, we have to add it to the other side. And I think this is full circle now, that this function, this isn't just function of x is something something x. We're setting this value to be 0, so this is something something x that makes this 0. So this has to be just one value. And now we have something that's balanced. We have an equation that's balanced. If this is 0 something something x plus 2, we can say this is negative 2 something something x. Now we're balanced. Cool. Alright, I think I'm almost done, but we're going to go back to this equation where we had x squared plus 4x plus 3 is equal to 48. And now we're going to complete the square in the way that I did in the video. We're going to x squared plus 4x. And now get this to the other side. That's going to be 48 minus 3 is 45. Cool. Now we're going to complete the square over here. We need x plus, we need this to be 2 because it's half. You know, and let's just do this, and then, you know, forget about that term. Just the axiom is like, hey, you need an x. This has to be x squared. You get that. But then if you have this, it's got to be, and let's just try it out. Even if you don't know the rules, just kind of experiment. And now we're going to do this. It's going to be x squared plus 2x plus 2x, just kind of foiling my way through, plus 4. And this is x squared plus 4x plus 4. Sweet. So that is, when I square this, I get this. But I didn't have that to begin with. You know what I mean? So I have to add 4 here, and then I have to add 4 here. Cool. So when I add 4 on both sides, then we're just money. If I knew right off the bat, I could have done this. I could have said x squared plus 4x. I need a 4 here. Let's take 1 from the other side. Plus 4 is equal to 47. I feel like this is not working out. What? Oh, never mind. If I add 1 over here, I got to add 1, 49. Yes, there you go. So, yeah, 45 plus 4 is 49. So that was adding 4 on both sides. If I just had this and I know I needed 4 right here, well, I must just, you know, to make the equation balanced, I got to kick that one up. I don't know, you know what I mean? So I think this was a good video because you're answering it just by examples and some visual examples. And so I thought that was kind of cool. Let's go back on that last one, though, because it's just kind of fascinating. Like, let's see what we get. We get x plus 2 squared. What do we get? X plus 2 squared is equal to 49. Okay. Were we satisfied with that? I feel like we're missing something. No, this is just when we throw in 5 in here, we get 5 plus 2 squared is equal to 49. So that it just satisfies the expression. So if we didn't know that x, we just chose x to be 5. I forgot that that x value was the unknown. We didn't know what x was going to be, but we knew what the area was. So that's the same thing with the quadratics, what we were doing. We didn't know what the time was when this hit the ground, but we did know the location that it was going to hit the ground. So if this was a function of time, we did know this height was going to be 0. But we were just taking one where I guess we already set our value for x and we knew our area. So we knew both sides of the equation. We were just showing how that we can complete the square to get... No, something's wrong here. So, holy Toledo. All right, so this should be x. This should be 7 squared is 49. Our area was only 48, so we should have a -1 right here. Let me turn off the camera and see what gives. All right, hell yeah. So hopefully I'm not confusing, but I'm sure I am. So this was our equation for our area. And when we throw in x equals 5, we get this area. But we can rearrange this equation, and we're just assuming, hey, if we had a 4 here, then we could complete the square. We would have x plus 2 squared. But that's going to overshoot our area. That's going to be an area of 49, which is not equal to 48. So we have to back this off by 1. You know what I mean? Because we only had +3, and I'm just kind of assuming that we have a +4, but we don't. And so, yep. Because even when I took this 3 to the other side, it was 45, and then I had to gain 4 right here. Well, I would have had to gain 4 over here, and we would have had 49. So this new area would be 49 if I took that as my square. I know my area is 48, so I need to subtract 1 from both sides to get back to that original area. Wow, that sucked. But anyway, I'm satisfied that it showed completing the square. And the other thing that I'm satisfied on is that, we have x plus 1, x plus 3. It also showed that our equation for the area is also x plus 2 squared minus 1. So if we have 5 and then 1, 2, 3, and then we have 5 and then 1, if we have x plus 2 right to there, x plus 1, 2. So now these two things, so this area right here is 48. This area right here is x plus 2, but then we actually have to subtract 1 block. So this area right here is 49, but subtract 1 of those blocks, that's going to give us the area of 48. Area 49 minus 1. So that's 49 minus 1. And that's so just another way to represent the area of 48 with squares. Sweet. And let's go, finally, let's just do that other one. We have x plus 1. That's going to be x plus 1 squared. This is going to be 6 squared. Heck yeah, 36, but we have to add 12 to get up to that 48. Okay, so, all right, and now I actually see where my mistake was. Because if we don't have anything here, and then we complete this square, we actually gain this term. But this term gets absorbed into the completion of this square. So, and so this is actually written wrong. You know what I mean? We don't just add it to this side, add it to this side. This term right here is inside this. So we have this is an incomplete square. When we complete the square, we gain this term. So if we FOIL this out, we're going to have that x squared. And then we're going to have that term, b squared 4a squared. And then you're going to have the middle term, which is just this times this, but 2 of them. So we have x, bax. And then over here, we're going to gain that term, negative ca plus b over 4a squared. But that's where I was just like, oh yeah, no duh. So this term is our square term, x plus something squared. But then over here is our original. This was the area of 48. Cool, we have 48, but then we had to add that to this side. That's where that plus 1 came from, and that's why we have to subtract that from the other side. And so, man, I'm just kind of running short on time, but now I'm kind of understanding. Man, I want to do it one more time. 1, 2, 3, 4, 5, and then 1, 2, 3. All right, booyah. 1, 2, 3, 4, 5, and then 1. It's a pretty decent example. And so, yeah, so we have x plus 3, x plus 1. When we do it, we're going to get x squared plus 4x plus 3. This is the equation, and this is going to equal 48. All right, so let's run through that whole process. We're going to go x squared plus 4x, get the 3 over there. So that's going to be 45. We're going to subtract 3. Now we're going to complete this square. We're going to get x plus 2 squared, and then the second you complete this square, like FOIL it out, because your term's going to be totally different. Now we're going to have x squared plus 4x plus 4. So yeah, write that out. We have x squared plus 4x plus 4, and so now we actually have to add that to the other side. 45 plus 4. Cool. Now, and then, yeah, so this was the missing kind of link, is to like, when you get here where you have where you can't make the square, but then you complete the square, then FOIL it back out, and then refoil it. I mean, just like get it back to this form and go x plus 2 squared. That's this term, this whole term, and then subtract the 4. And then this is going to be equal to 45. Booyah. And it's a little bit funky for the, because we actually have a value right here, and this was our area, and then we took everything to the other side. So if we have to get this value back up to 48, we would go 45 plus 3, and we would go plus 3 on this side. So then we'd have x plus 2 squared minus 1 is equal to 48. Okay, hell yeah. And I guess that's just showing that, hey, if we have this polynomial is equal to this area 48, I can represent it as a square. X plus 2 squared minus 1 is equal to 48. And it's kind of fascinating that I could represent it in more, so the take-home point for me is like, whoa, I could represent this in more than one square. But that's only for this problem, though. It just says that x plus 1 and x plus 3 can be similar to, well, I don't know. This is really fascinating me. Can you have... Yeah, so we said that we could have x plus 1 squared plus 12. You know, if we increase this to x plus 3 squared, we're definitely going to have to subtract a bigger number to get back to that area of 48. But yeah, you could have different square components here. And then, yeah, this is just your constant to balance the equation, just to make sure whatever you do here as a function of x, and it still doesn't change the value of what x is. X is still equal to 5. So, yep. So that, I'm just going to leave it there, because there's other things. I want to make a video of, like, you know, this video showed that, hey, if you get a value over here, something, something x, it is balanced. So if you have plus a constant, then you're going to have 0 minus that constant, something, something x. Now it's still balanced. One of the videos that I want to make is... the fact that if you have like 1 over 2x plus 1 over x squared plus 5 is equal to 0. What you can't do is you can't just come in here and square each term. You can't do that. You can square the whole thing, but that's not going to be helpful. So I think that's kind of the one way to end it, is just like, yep, you can do individual things. So you can't do that. You could square the whole thing. You could come in here and I don't know, and there's not much else you could do. Well, you could multiply everything by x squared. Yeah, so as long as you do that, and then you have x squared over here, So you can do that as long as you have a value here, you know what I mean? So that was kind of the take-home point. Is like, do we have a function, or did we evaluate a function at a certain value, and then we're solving for, you know, and I'm bad at, like, you know, independent, dependent variables. But anyway, the other number is also a value that makes it all balanced. And then I guess the last one to leave it on would be to where you have like 1 over x plus 1 minus 1 over x plus 2. Like, how do you, like, what can you do to this? You know what I mean? Get your denominators the same by multiplying by x plus 2 and then x plus 1. And then, but you have to do the same thing to both sides. Like, this is just like multiplying by 1. So even though this is equal to 10 over here, like it seems like you would have to do this to every part of the equation, but no, you're just multiplying by a ratio of 1. But this is only a strategy to get the denominators the same, where then you can add these. So if you added these, it would be x plus 2 minus x minus 1, and then you would have 1 over x plus 2 x plus 1 equals 10. Like, you know what I mean? If that was something that you wanted to do, you can do it. You know what I mean? You know, sometimes that can be helpful. At least you have one term over here, and we can even FOIL that through. You're going to have x squared plus 3x plus 2 is equal to, so you have 1 divided by, and then that's equal to 10. And you can, you know, then you can get this upstairs. So this is your classic, especially with square roots. Heck yeah, you get this a lot, like 1 divided by 2x plus 1 divided by x squared plus 5 is equal to some number 10. And you're like, what do we do with that? Well, let's make this 10x squared. This becomes, so multiply everything by x squared. This becomes 1/2 x, this becomes 1, and this becomes 5x squared. Cool, now it's a polynomial. Sorry I'm doing this real fast, but hell yeah. Then you get this upstairs. You have 1 on this side is equal to 10x squared plus 30x plus 20. You know what I mean? So just different ways to get it into a form. I gotta go, so thanks for joining me on this. This was fun though. I don't know, probably not. Probably not a very good one, but thanks for joining me, and that's a video.